Well, let's begin here. I should mention, before we continue this example, that with this example, you should be able to find also, in addition to sigma sub x bar and n, you should also be able to figure out what the critical value is based on this. How would you do that? Well, at least based on this more accurate approximation that comes from these equations, this is the value then you'd report. But based on this more accurate approximation to the solution of these equations, you could take that number and plug it into, for example, well, never mind, you can take this number and you can plug it back into here, for example, multiply it by 1.645, and then that gives you the critical value. So let's go ahead and do that. By the way, you want your calculator out if it's not out here. You take 1.645 times 0.341880, I can't quite see it, 341? 341 what?
No.
You get a critical value for the rejection region of about 0.56. Actually, in real life, that's the solution of the equations. Actually, in real life, you would use n equals 35, which would then change sigma sub x bar, which would then change the critical value, but don't worry about it. Okay? But as far as what I would probably ask you, I guess I said you should be able to do this. I probably would just focus on n. So I guess I changed my mind there in the midst of doing that problem. But in real life, you should be able to find the critical value too. All right, coming back now to the proportion problem, you will want to keep your calculator out. So we were trying to estimate the difference in the population proportions P1 minus P2, where these sentences essentially, or this sentence defines both P1 and P2. I could ask you to define those, though if I did, in this problem, since it's less clear, I'd maybe have to give you some suggestions or something, I don't know. It's more clear in some problems. Again, what's not clear is it seems like maybe we're looking at population data instead of sample data. It depends on how you think about it. So let's go ahead and calculate this confidence interval. Let's make it a 95% confidence interval, which will make z star 1.96. I guess in the directions I didn't say what confidence level to choose. Well, let's do it a different one. Let's do 99%, just for some variety. What's P1 hat? P1 hat, look at the numbers, is 16 over 414. That is an estimate for the fraction of all birth defects that occurred from women who drank the contaminated water. 16 over 414.
1.0386.
Yeah, we'll see it on the calculator too. P2 hat is 3 over 228. Yeah, P1 hat 16 divided by 414. That fraction, that proportion is about that. Is that what you got? 0.0386. Again, if you were just reporting this number, you'd want to round probably to 3.9%, most likely. But for the sake of not having errors propagate, only round your final answer so the errors don't propagate and get bigger and bigger. Go ahead and keep more decimal places. It's probably a bit paranoid to keep all of those, but I think this is a good place to be paranoid. All right, we don't want to think about the nature of propagating errors in here. We've got enough to do as it is. So just keep as much decimal places as your calculator gives you, a typical graphing calculator, when you write those down here for the purposes of ultimately doing the final calculation and rounding at the end. 3 over 228 is a smaller proportion, about 1.3%. 0.0131578947. Your point estimate which, by the way, sometimes the book calls D for difference. Difference, which they do with proportions, they don't do it with means. I think that's actually standard for some reason. The difference of the proportions, sample proportions, P1 hat minus P2 hat, do the subtraction. Take 0.0386473343, subtract 0.0131578947. There's the difference, about 2.5%. Go ahead and include all the decimals. If you were going to report it, you'd want to round it to 2.5%. It is a positive number, giving us some evidence against the null hypothesis that P1 equals P2. But would it be statistically significant evidence? We're not sure yet. What's Z star for 99%? You got to go to, well, the quickest way is with table D. Going to the table, or excuse me, yeah, table D. Going to the bottom, and you can't really see it here. That's a 99%, 2.576, you're right. 2.576 is the Z star for 99%. You don't have to worry about degrees of freedom here. 2.576, let's go back to the problem. What's the standard error? Do this with me on your calculator. I am going to kind of do a bunch of things at once. You want to write down the intermediate numbers. Let me go ahead and retype them in as fractions again. 16 divided by 4, 14 is that. That's P1 hat. If you want to multiply that times 1 minus P1 hat, you can do this. You can do times, in parentheses, 1 minus A and S. Maybe you know that trick already. Oops, get a minus sign in there. So that's P1 hat minus P2 minus 1, or times 1 minus P1 hat. It's that. You might want to write that number now down. You're going to divide that by 414. You might want to write this number down. Certainly, write this next number down. It's going to be pretty small, probably in scientific notation. 8.974 times 10 to the negative 5. You can write it in scientific notation on the test. You can also write it with as 0.0000, 4 zeros, then 897432991. You move the decimal point to the left 5 spots, and that would give you 4 zeros after the decimal in front of the 8. I'm not going to take the time to write this down because we've got to get to the more general review here. Let me go ahead and add this to the other one all at once. So this will take some typing. Plus, the other fraction is, okay, I guess I could use parentheses. 3 divided by 228. I don't recommend doing it this way in the test. I'm doing it for the sake of time. Times 1 minus 3 divided by 228. All divided by 228. That should work. That really does divide the entire product by 228, even though it looks like I'm only dividing the second thing by 228. This should work if it does order of operations correctly, as it should. I'm guessing something to the negative 4 power. Yeah, okay, that makes me feel good. That's the thing that goes under the square root. Something times 10 to the negative 4 power. Take the square root of that, you can raise it to the 0.5 power. There's your standard error. Write that number down. This is the thing you'd multiply by, what was it, 2.576? Times 2.576 to get the margin of error. Ready? There it is. 0.031. Now go ahead and round. It seems our 99% confidence interval is approximately that number, rounded to say 0.025, plus or minus, again, really you should round to the same number of same amount of precision in your margin of error as your estimate, but I like rounding to one more because it just feels good. You shouldn't really do it in a report that way. 0.031 is how you should really round it, but I'll go 1, 2. So there's the plus or minus notation in interval notation. 0.025 minus 0.0312, negative 0.0062, I think. Somebody check that?
Yeah.
To positive 0.0562. Right? What's the important point about that interval? The most important point about it is that it contains 0, meaning it contains both positives and negatives. So we got some evidence against the null hypothesis that P1 and P2 are equal, but not really strong evidence. It's close to not containing 0. If we were doing a two-sided test, well, this doesn't quite match the two-sided test because of an extra tricky thing that happens. If we were doing a two-sided test that P1 and P2 are equal, we would not quite have strong enough evidence against the null at the 1% level of significance, but maybe we would at the 5%. So as far as wanting to sue those responsible, it's maybe sort of a boundary case as far as we can tell. Although again, maybe this is not the best situation to apply inference. Definitely, if these numbers are population numbers, definitely people who drank contaminated well water had birth defects at a higher proportion than those who didn't. If these are really the population to think about. I don't know. I'm not enough of an expert, and we don't know the full situation here to know for sure about that. But if you're thinking in terms of all the women who could have drank from these wells and could have had babies but didn't, maybe we don't quite have strong enough evidence against the null that the proportions are equal. We're not going to worry about those kind of details. All right, for the rest of class, we're going to focus on a general review. We have to go pretty quickly, so I can only highlight things in a kind of shallow way with the time that we have. So you're going to want to definitely study things in more depth than what I have time to say, but I think it's worth saying anyway. In the PowerPoint, I've got a list of things to know from chapters 5, 6, 7, and 8 that I'll go through. I also re-put up there the list of things to know from chapters 1, 2, 3, and 4. Especially with the older chapters, I will try to pick certain things that might be more likely to be on the test than not. I'm probably going to start writing the test this afternoon, and so this is sort of my initial thinking about it. Yes? Chapter 5, that was about probability. Theoretical probability rules. They have names. The complement rule, the addition rule for disjoint events, the general addition rule, the multiplication rule for independent events, conditional probability, and a formula for conditional probability, general multiplication rule, and Bayes' rule. Lots of rules there. Maybe I'll highlight perhaps the most important one, though these are all important. And that's the multiplication rule for independent events is perhaps the most important. If A and B are independent, the probability that A and B occur in a given situation, if they're two independent events, unrelated events, is the product of their probabilities. That's the multiplication rule for independent events. The general multiplication rule says that, well, change this one to a conditional probability. That always works. And it works even in the case where A and B are independent, because when A and B are independent, this equals the probability of B occurring if A and B are independent. And that should make intuitive sense. If A and B are independent, they're unrelated. Knowing that A has occurred doesn't affect your assessment of the probability that B has occurred. Now, what happens as far as typical usage of this formula? Typically, we do use the formula in the independent form in the following kind of way. We often are encountering situations in real life where it seems reasonable to assume events are independent. So when I'm talking about that, I'm talking about situations that are not about cards and not about dice. Well, I guess you could do it with dice. It's not about cards and wondering are getting a queen and getting a red independent or not. It's about a situation where maybe you've got for example, some backup, a regular computer server and a backup computer server, and you're wondering how trustworthy they are when they are used independently of each other. Like, what is the chances that they both fail? Based on one of them being 99% reliable and the other one being 98% reliable. So the first one fails at a rate of 1% per day. There's a 1% chance on any given day it's going to fail. And the other one fails at a 2% rate. There's a 2% chance it's going to fail on any given day. What is the chance that on a given day they both work? This one and the other one. For the independent assumption to be valid, maybe they need to be in separate locations so that they're working or not independently of each other. You calculate the probability of one working times the probability that the other working to calculate the probability that they both work. One and the other one. The hardest one is probably Bayes' rule. That could come up on the test, so you want to practice it. That's where we make the tree diagrams. There is the formula for it, but I think it's better to do it in terms of the tree diagrams. You can look at the old video where we did a problem like that. If you want to take the time to watch that and try to remember how to do it. The tree diagram really helps you think it through and think about why it makes sense. Binomial random variables and Poisson random variables are the other main topics. Chapter 5. What's the binomial setting? What's the Poisson setting? Well, those are kind of technical. Binomial is easier than Poisson as far as the technicalities of the setting. With binomial, you've got a certain fixed number of trials n in a certain situation where you're doing something over and over again n times. You've got a certain fixed probability of success, like, say, shooting a free throw, okay? In a non-pressure situation. That's sort of the most ideal situation to apply a binomial random variable. You're going to try shooting a free throw 20 times, nobody's around, no pressure. Your probability of success is basically the same each time. And since there's nobody around, there's no pressure, each trial is independent of what happened before. In a pressure situation, that might not be valid because if you've missed a few times in a row, you start feeling nervous, maybe more nervous, and it affects your ability on the next time. Maybe, maybe not. Okay, though people do try, even in pressure situations, to apply a binomial random variable. That probability of success, you assume, stays constant from trial to trial. N might be 10 or 20 or 30. P might be 0.7 or something for free throws. 70% chance. Though for me, it's only 40%. I kept track of my free throw percentage over the years when I don't have a pressure situation, and I'm only about a 40% shooter. You saw what happened last time, right? Yeah. You should be able to use the formula, which involves the binomial coefficients n choose k. You should be able to use the factorial formula and show your work with cancellation. We've done that before. You should also be able to use your calculator to find the answer quickly if you need to, or check your answer. Okay? I'm not going to write down the formula for sake of time. N choose K, I'll just say it. N choose K. With the funny notation with the parentheses and no fraction. Or use the NCK notation if you prefer, which is what the calculator does. Times P to the K, where K is the number of successes you're thinking about, and P is the probability of success, times 1 minus P to the N minus K. 1 minus P is the probability of failure. N minus K is the number of failures. I'm quickly saying this verbally. I don't know if you're tracking with me. Look in the book for the formula. Try to recall it from memory, okay, when you're practicing these things. Poisson random variables, the Poisson setting is more technical. Don't worry too much about the technicalities of it. I guess anytime I give you a situation where you're counting the number of successes, and the number of successes doesn't really have a natural upper boundary, as far as how big it is, there is no n, I will make it a situation where the Poisson setting is reasonable. If you're counting the number of successes, the formula for the probability of k successes involved the number e. It involved mu, the mean number of successes based on past data that you would use to come up with your model. So you should be able to use that formula, and not just one time, but maybe if you're trying to figure out the probability that x is less than or equal to, for example, 2, you should be able to use the formula multiple times to add up these probabilities. In this case, you have to use it 3 times. The probability of getting 2 or fewer successes, quote unquote, success could be bad, like an earthquake happens, is the probability of getting 0 successes plus the probability of getting 1 success plus the probability of getting 2 successes. Use the formula in each one of those cases and then add the results, which really means you're using the addition rule for disjoint events when you do that. Gotta go quick here. Chapter 6, fundamental ideas of statistical inference. All these situations we're assuming we know sigma, the population standard deviation, which again is not practical, but the chapter is hard enough as it is to get the basic ideas down that we assume we know sigma. So we use a confidence interval to estimate a population mean. When the population standard deviation is known, x bar is the point estimate, plus or minus the margin of error. The margin of error is a special number, which in chapter 6 is a z star when you know sigma. Population standard deviation times sigma sub x bar at sigma over square root of n. Got this in your mind? No time to write it down? Tracking with me? You got to be thinking, okay? Imagining, remembering. And then hypothesis testing in that situation, also called test of significance. Typically, actually, just a little historical thing here, quick. Hypothesis testing is the old name. That's the name people have typically used in the past when they are focused on alpha and a critical value of z and a critical value of x in a rejection region, which you have to know if you're going to calculate the power and the probability of type 2 error. More recently, they use the phrase significance testing when they focus on the p-value. You can relate the two. If the p-value is less than alpha, then you reject the null. You say you have statistically significant evidence against the null at that alpha. However, sometimes, in more recent years, people just report the p-value. And maybe they don't actually make a decision. They don't say, we're going to reject the null or not. Maybe they just report the p-value and say, okay, you decide. Are you going to reject the null or not? Or the community is going to decide. Either a business community, people in your company, or a scientific community in, say, a social science situation. It's just more pieces of evidence against a certain null hypothesis. They report the p-value. They don't say anything else. They don't say reject the null. That's a more recent kind of use, and in that kind of situation, they call it significance testing more often. But again, here the population standard deviation is known. You should be able to set up the hypotheses, define the parameters, do the test, calculate p-value, Or calculate the z statistic and decide to reject or not based on the z crit. You got to know alpha to find that. Okay. Probably, I mean, you should be able to do both. You should be able to do a two-sided test with a confidence interval. If the null value is in the interval, then you don't reject. If it's a 95% confidence interval for a two-sided test, you don't reject at the 5% level of significance. If it's a 90% confidence interval and the null value is in there, you don't reject at the 10% level of significance. If the null value is not in the interval, then that is statistically significant evidence against the null, and you do reject at those levels. I know what I'm talking about in a minute. Sorry. Cautions about statistical inference. One big caution that comes into my mind is if your sample size is large enough, you will almost always reject the null. You'll almost always, with a really big sample size, find statistically significant evidence against the null. The p-value can end up being typically pretty small if n is really large. However, just because of that, that doesn't mean it's important evidence against the null. Maybe it's just a small difference. Maybe x bar is not very far from the null value of mu. And so even though the p-value is really small, maybe it's not an important difference to be able to worry about. So maybe even though you could say you reject the null, it's not worth rejecting. It's not an important difference that you found. That's one big thing that comes to my mind when I think about cautions. Another big caution is all this stuff only works when you're doing simple random sampling. These formulas, technically speaking, only work when you're doing simple random sampling. When you're not doing that, well, if it's bias sampling, everything is out the window. Don't do this kind of stuff at all if you're doing bad sampling. If it's some sort of other probability sampling with some kind of randomness, like a stratified random sample, there are formulas that help you do things and do inference, but technically speaking, they're more complicated and we're not talking about them. We're talking about the simplest kind of situations. If it's close to random sampling, then you sort of hope your formulas are pretty good and you're fairly happy with them. Otherwise, you call your local statistician. Okay? Power test, type 1 and type 2 errors. I think I won't talk about that anymore today because we talked about it plenty recently, and so watch the recent videos for that. That could come up on the test. This type of problem could come up, though I'd give you a help with it if it was on the test. Or maybe a simpler power calculation where I tell you what n is and what the rejection region is, perhaps. And you need to figure out the power or the probability of type 2 error in that situation. That would be a simpler kind of power calculation. We did that. Chapter 7, more realistic inference about population means, confidence intervals, and hypothesis testing for one population mean based on one random sample, one sample t-statistic, or confidence intervals and hypothesis testing for comparing two means from two populations based on two independent samples, possibly of different sample sizes. Use the two-sample t-statistic with the conservative approach to degrees of freedom. Don't need to use that Smith-Satterthwaite formula. Don't need to use software on the test or your calculator. We'll use the conservative approach. Take the smaller of n1 minus 1 and n2 minus 1. Not the larger. The quiz was larger. That was a false thing. It's the smaller of the two. And then the chapter 8 stuff, proportions, one population, one sample, two populations, two samples, two independent samples. With the two populations and two samples, we're just doing the confidence intervals like we did today. We won't do the hypothesis testing because that adds an extra layer of complication. We'll wait for 1 week from today after the test to talk about that. What about older stuff? Chapters 1, 2, 3, and 4. Yeah, I do have chapter 8 stuff here. I'm going to skip it. What comes up in my mind is perhaps the most important things from chapters 1, 2, 3, and 4 that could be on the test. Well, certainly I think any kind of typical old quiz multiple choice question about that stuff could come up. since the quizzes are cumulative and they're all multiple choice true false, I could see putting old, slightly modified quiz questions on the test about all those topics, so that really covers all main conceptual ideas from chapters 1 through 4. So probably the best approach there is study all the quiz questions and think about them. As far as calculations go, you should be able to certainly calculate means and standard deviations with your calculator. Probably won't have to do it by hand. So calculator usage there in chapter 1. Normal curve ones, you know, we do so many normal curve calculations from chapter 4 on that I don't think we have to put one that was from chapter 1 on the test. But we're doing plenty of normal curve calculations, and you shouldn't forget, for example, the 68, 95, 99, 47 rule. Chapter 2, there's something where calculations could come up, but probably not real detailed formulas where you have to use tables. Probably the book shortcut formulas, for example, for the slope and intercept of a regression line, when you know the correlation, you know the x bar, y bar, you know sx and sy. When you know those 5 numbers, there were the shortcut formulas that the book focused on. You might have to use those to find the slope and intercept B0 and B1 and B0. All the SS formulas, I probably won't do that for this exam, maybe on the final, but probably not for this exam. Focus on the shortcut formulas and focus on being able to use the regression line and to find a y hat and calculate a residual like for today's quiz. For you guys. Know the concept of the sum of the squares of the errors SSE. Maybe be able to calculate that. SSE, remember that? Not the other SS's, but maybe SSE. Sum of the squares of the residuals, errors. More general facts about regression. Chapter 3, probably just true, false, multiple choice type questions. That was about sampling, both for surveys and for experiments. Chapter 4 is about probability. The basic idea of probability could come up true, false, multiple choice question. Any calculations there? Yeah, I think probably you should certainly know how to calculate the mean and standard deviation of a discrete random variable with those formulas, the summations. And know the properties, the abstract properties of mu sub x plus y and sigma sub x plus y in the case where x and y are independent. Those are the main things that stand out besides the basic idea of probability. There's the central limit theorem. That's in chapter 5. Law of large numbers. Those are important. Okay? So I know I did this real quick. Watch the video again if you need to. Start studying.